You ever stop and think about that little zap you get from a doorknob? And then think about a massive, terrifying lightning bolt? Well, what if I told you they're basically the same thing? Yeah, just on a wildly different scale. We're going to break down exactly how that works.
Oh, you know the feeling. We've all been there, right? You're walking across a carpet, maybe in your socks, you reach for a doorknob and zap! You get that little shock. It's so normal, we just kind of shake it off and forget about it.
But here's the crazy part. That exact same science is responsible for this. A mind-blowing billion-volt blast of pure energy that can literally tear a tree apart. So the big question is, how on earth do you get from a tiny little finger zap to a sky-splitting lightning strike? Well, that's exactly what we're about to dive into.
Okay, so to really get a handle on lightning, we have to start small. We've got to go back to that zap, and it all boils down to one core idea: static electricity.
Right, and the key word here is right in the name, static. It literally means it's not moving. It's stationary. This isn't like the electricity flowing through the wires in your house. Nope, this is a charge that just builds up on a surface and sits there, kind of waiting for its moment to jump. The whole thing is just about an imbalance of electrons.
Someone on Reddit actually explained this perfectly. Think about it like this. You've got an aquarium with a divider right down the middle. Now you start pumping water from one side to the other. You're building up this difference in water levels, right? One side is high, one side is low. Well, nature absolutely hates that kind of imbalance. So the second you yank that divider out, whoosh, the water rushes back to even things out. That sudden rush, that's the zap.
Okay, so we've established there's an imbalance, but where does it even come from? I mean, how does a charge build up in the first place? Well, you can think of it as a tiny microscopic robbery. And this is how it happens. It's called the triboelectric effect. Every time you rub two different things together, like your socks on the carpet or, that classic balloon on the sweater trick, you're literally scraping electrons off of one surface and sticking them onto the other. So one thing ends up with extra electrons, that's a negative charge, and the other thing is now missing some electrons, which gives it a positive charge. Simple as that.
Now, this is where some people get a little mixed up. You might be thinking, hang on, I thought insulators were things that don't conduct electricity. And you're totally right, they're not good at it. See, in a conductor, like a metal doorknob, electrons can zip around all over the place. But in an insulator, like the rubber sole of your shoe, those electrons are held on tight. They can't really flow through the material, but they can absolutely get piled up on the surface. And that's the secret to how an insulator can hold a static charge.
All right, so we've got the basic idea down. Rubbing stuff together creates a charge imbalance. Now, let's take that concept and blow it up to an epic scale. I mean, way, way up. Forget about socks on a carpet. Let's talk about a storm cloud the size of a city. So picture the inside of a massive thundercloud. It is pure chaos in there. You've got warm, wet air shooting upwards. Those are the updrafts. At the same time, you've got cool air and rain falling down, the downdrafts. It's like a giant, violent blender in the sky where tiny little ice crystals and water droplets are just smashing into each other over and over again. And what happens when you have billions and billions of tiny particles rubbing against each other nonstop? You guessed it, the triboelectric effect, but on a massive scale. All those little collisions are stripping away electrons. And what happens is the lighter, positively charged ice crystals get swept up to the top of the cloud. Meanwhile, the heavier, negatively charged droplets and hail sink down toward the bottom. And just like that, the entire cloud has become a ginormous, floating battery in the sky.
So now the stage is set. You've got this massively charged cloud with a huge negative charge at the bottom. And the ground below it? Well, it responds by becoming positively charged. The only thing separating them is the air, which is an insulator. But that insulation is about to have a very, very bad day. You see, a lightning strike isn't just one big flash. It's actually a super fast four-step process. First, an invisible channel of negative charge, called a stepped leader, starts snaking its way down from the cloud, kind of feeling out the best path. As it gets close, the positive charge on the ground starts reaching up from things like trees or buildings. We call those ground streamers. Then, one of them connects with the leader, and boom, the circuit is complete. And here's the wild part. The bright flash we actually see, the return stroke, surges up that channel from the ground all the way to the cloud. Here's another way to think about it. That invisible stepped leader, it's like a scout, mapping out a jagged path on its way down. Then the bright return stroke is like the main army, racing up that path the scout just created. That's what lights up the sky. So that classic zigzag shape of lightning, it's really just the ghost of the path that the invisible leader took a split second earlier. And the amount of energy we're talking about is just staggering. The air inside that narrow lightning channel gets heated to 50,000 degrees Fahrenheit. Let me say that again, 50,000 degrees. That is 5 times hotter than the surface of the sun. That intense heat makes the air around it expand violently, creating a massive shockwave. And that shockwave is the sonic boom we hear as thunder. But, it's not all just about those classic cloud-to-ground strikes we always see. Nature's got a whole exotic menu of weird and beautiful electrical shows that are, frankly, even more mysterious. So most of the lightning we see, like 90% of it, comes from that negatively charged bottom part of the cloud. But there's this other rarer kind that comes from the positively charged top of the cloud. And because it has to travel so much farther to reach the ground, it needs a lot more juice. We're talking up to 10 times more powerful. This positive lightning is the really dangerous stuff because it can strike over 25 miles away from the storm itself. People call it a bolt from the blue for a reason. And if you think that's strange, it gets even weirder. Way, way up above the storm clouds, in the upper atmosphere, there's this whole other light show going on. We're talking about these incredible, almost ghostly discharges. You've got sprites, which look like giant red jellyfish bursting up toward space. There are elves, huge glowing halos of light, and blue jets, which are cones of blue light that spray upwards from the tops of the clouds. For years, people thought these were just stories pilots told, but nope, they are very, very real and a stunningly beautiful part of our planet's electrical system. So, as cool and fascinating as all this is, we absolutely have to remember that lightning is also incredibly dangerous. So let's bring this all back down to Earth and talk about some essential safety. Globally, about 24,000 people are killed by lightning every single year. That's a pretty sobering number and a huge reminder of the raw power we're dealing with. Now, your personal odds of getting struck are pretty low, but the consequences are so severe that knowing exactly what to do is absolutely critical. And the rules for staying safe are actually really simple. The big one is, when thunder roars, go indoors. Just get inside. Stay away from open fields, tall trees, and water. And once you're inside, try to avoid plumbing and electronics that are plugged into the wall. And listen, this part is so, so important. If someone is struck by lightning, they do not hold an electrical charge. They are completely safe to touch, and you need to perform CPR right away. It's truly the most important thing you can do and could save their life. So we kind of end up back where we started, just looking at this incredible force of nature. On the one hand, it's this terrifying, destructive power. But on the other, that same intense energy blast actually does something amazing. It splits nitrogen molecules in the air, which then fall to the earth in rain as nitrates. And nitrates are basically a natural fertilizer that's essential for plants to grow, for all life, really. So what is lightning then? Is it a destroyer or is it a creator? That's something to chew on the next time you hear that thunder start to roll.